Right. Good afternoon, everyone. My name is Thomas Weiner. Let me just mention my colleagues and co-authors. This is Wolfgang Böhme, who just left for his well-deserved retirement 3 months ago, and Johannes Stadlik. We're all from the Fraunhofer Institute for Mechanics and Materials, IWM, in Freiburg, Germany. Just to give you an overview of the content of this talk, I'm going to give you a short introduction and background of the master curve concept according to the ASTM standard. I'm going to talk a bit about the materials and specimens used, about the experimental test lab for those dynamic tests, and then mention a bit about the master curves at those elevated loading rates. Yeah, we're going to go a bit more into detail about an effect which plays a significant role here, which is the adiabatic heating, and we'll finish with some conclusions. This work presented here is based on a joint research project by MPA Stuttgart and Fraunhofer IWM. Uwe Meyer from MPA Stuttgart will give another talk this afternoon presenting as well results from this joint project. So the background is nuclear safety research, basically for a safety assessment, as well as accidental loads which could result maybe from a plane crash, earthquake or explosion, have to be considered, and thus the database, particularly for the fracture toughness values, have to be extended. There are two concepts which could be applied for a process for a fracture mechanical safety assessment, and which are applied as well for process-static loading. First of all, that would be done in a deterministic fashion. You could use K1C and K1R reference curves according to the ASPE code, and then there's a probabilistic approach, so-called master curve concept, developed by Kim Balin, which I've spotted as well in the audience, and which gives us the possibility to determine lower bound curves from a probabilistic approach. For example, we could use the 5% lower bound curves for a fracture assessment. The concept allows as well then for a certain amount of plastic deformation and ductile crack extension before the cleavage actually occurs. So just to present the concept here, master curve basically describes the statistical distribution and the temperature dependence of the fracture toughness values in the lower shelf and in the ductile to brittle transition zone. In a general form, it's written like here. The orange part describes the statistical distribution, and the green part the temperature dependence. So putting in now values, for example, for the median curve, a probability of 0.5, 50%, and according to the ASTM standard for ferritic steels, we assume a Weibull distribution with a minimum K value of 20 megapascal square meter, and Weibull coefficient B equals 4. We get this more commonly seen formula for the master curve, median master curve. Parameter P is here set to 0.019, which determines basically the shape of this curve. And the only parameter which is left is T0, which is the master curve reference temperature. So this is basically the temperature where the master curve reaches 100 megapascal square meter. So this concept can be applied as well for higher loading rates. Basically what happens at higher loading rates, we get an embrittlement, a so-called dynamic embrittlement, which reduces the fracture toughness of ferritic steels. And this can also be described in the master curve concept with a shift of the master curve to higher temperatures. So you end up with a different reference temperature, here denoted with T0x, where x stands for the logarithm of the crack tip loading rate. We used the material 22 neochromium 37, which we got from a reactor pressure vessel which was never really in use, B+C, and we extracted SLB specimens which were tested at IWM, and we extracted CT specimens which were tested at the MPA in Stuttgart. The cracks were assumed to run from the inside to the outside and in the TS orientation. Just to give you an overview about the dynamical test equipment, unlike in a quasi-static situation, you can't just simply use, for example, the global force in order to determine the fracture toughness values from your specimens. You basically would get for this velocities of 2.5 meters per second, for example, just the inertia peak. So what we do instead is using a local force measurement. We basically apply strain gauges close to the crack tip and translate that with a calibration routine to a local force measured directly at the crack tip. Likewise, for the crack mouth opening displacement, we can't just simply use a clip gauge to measure the crack mouth opening displacement. This would just as well have as well inertia effects In our case, we used a high-speed camera and additionally digital image correlation to measure then the crack mouth opening displacement at our specimens. So you end up with the force and crack mouth opening displacement curves, and then the evaluation of the fracture toughness value kgcd, depending on the temperature and the loading rate, would be done in this standard way as it would be done with the quasi-static evaluation according to the ASTM standard. Now let's have a look at some results of two different loading rates. One here with 25 millimeter per second gives us a crack loading rate of 10 to the power of 3 megapascal square meter per second, and a higher loading rate here with 2.5 meters per second with a tractive loading rate of 10 to the power of 5 megapascal square meter per second, so 100 times faster. But both are faster than a quasi-static case. What you can see here now compared to the quasi-static median master curve is here the results for two test series at two different temperatures. The blue stands here for minus 20 degrees, green for 0 degrees, and at the higher loading rate, we've got an additional temperature at plus 20 degrees. What we can see here now is that there is definitely some embrittlement. We can determine delta T0 of plus 30 Kelvin for the medium rate, and for the high rate, and difference of 60 Kelvin. So there's an embrittlement. We've got the mass curve moving towards the right-hand side to higher temperatures. What we can see as well here is that there's a poor agreement basically on the master curve to our actual values. So you can see here the median values for each test series, and the curve doesn't really fit nicely to the master curve prediction. And you can see that as well if we determine the signal temperature estimates from each test series, that they don't agree well either for the low or the medium loading rate and the high loading rate. So what could be the reason for that situation that it seems that the master curve has to be a bit steeper or quite steeper? An idea is that adiabatic heating plays a role. So due to the deformation of the plastic zone, the crack tip is transferred to heat, and that cannot be dissipated in those such short times to fracture, which happen at elevated loading rates. So there has been done work already as well, for example, to mention Zender and Rosakis, who did as well investigate the heating around the crack tip with an infrared high-speed camera. And what that heat could do to the master curve is basically that it leads to a progressive increase. Basically, the higher the fracture toughness, the more you've got a larger plastic zone, which then leads to more heat generated. So you've got a progressive increase of the actual curve. So this can be as well described with a different shape parameter P. So instead of using just 0.019, we can use, for example, 0.03, and which would give us a steeper curve, master curve. This idea is not completely new. Already Schindler and Kalkov, 2012, mentioned that in a paper, and we did as well have a similar research project investigating that. So they suggested a loading rate dependent shape parameter P in order to account for this effect. If we apply now this changed shape parameter P, 0.03, now the actual master curve fits nicely to our experimental tested specimens and results. For the medium rate and as well for the high loading rate. This can be as well seen in the moving together of the two individual single temperature estimates determined from each test series. Here on this side and as well on this side. So we just wanted to go a bit further deeper in the situation and have a look at the actual heat generated at the crack tip. So we did some tests with a high-speed infrared camera and to measure the heat generated around the crack tip, and the second high-speed camera on the other side to measure as well the local strain field around the crack tip. And we used here specimens without side grooves just in order to have a better view on the actual heat generated. We did as well a numerical simulation of this test with Abacus Explicit as an input served flow curves, which were determined from dynamic round tensile tests in a wide strain range and in a wide temperature range. We had to adjust basically the flow curves in order to match the technical stress strain curves because we considered here adiabatic heating in the heat conduction and as well the local strain rate, which are not constant basically during the test. So after adjusting these, we ended up with a simulation result just right at the time before fracture occurs and can compare that to the experimental data. Here you see the Van Mises strain determined with the RMS system, so with digital image correlation, compared to the numerical analysis of with the meso strains on the specimen surface, and a quite good agreement between the simulation and experiment, as well, considering the fact that we can't really determine the strains right at the crack tip with RMS. Similarly, for the temperature, we've got a quite nice agreement between simulation and experiment. We measure up to an increase of heat around 80 Kelvin, which is as well predicted quite nicely by the simulation. So to conclude, we've done some dynamic tests with SAB 4020 specimens at a medium and a high loading rate. We observed some steeper master curves for dynamic loading when compared to the crash-static ones. The explanation for that are that the higher the loading rate and the higher the fracture toughness, the more an adiabatic heating plays a role and influences the fracture toughness. I've left out basically the explanation for that, what actually that means that a heated specimen or a heated area around the crack front leads to actually higher fracture toughness values. That still remains for future research. What I could tell is that we observed as well some local crack arrest phenomena along the crack front and in the stretch zone, which increases as well with temperature. So this can be an effect or explain as well that we've got as well higher fracture toughness with an increase in temperature. We've investigated this heat generated with an infrared camera and measured some value of 80 Kelvins increase in temperature, which was as well quite nicely predicted by the simulation. For an outlook, we're going to do some further experimental work and immersion investigations with some tests at several more temperatures and strain rates, and having a closer look at the actual adiabatic heat generated at the point of fracture on the specimen, which happens inside the specimen, not on the surface as we measured here. I'd like to acknowledge as well the funding done by the German Federal Ministry of Economic Affairs and Energy, and I would like to thank you for your attention. Thank you very much.